So in this first example, we've got x plus 4 over x cubed plus x dx. So that's a rational function. So it means that we should probably try to split it up using partial fractions. So I'll write x plus 4 over x cubed plus x, and the denominator factors as an x times an x squared plus 1. So this should split into fractions some a over x plus some bx plus c over x squared plus 1. Now we multiply both sides of the equality by this denominator, and we get an x plus 4 is equal to x cubed plus x times that a over x. That just becomes an a over x squared plus 1 plus a bx plus c times x. And now we can expand everything out. So we've got an ax squared and another bx squared, so that's an a plus bx squared. And an a and a cx, so that's a plus a cx plus a. And the coefficients have to equal each other if these are to be equal as polynomials. And so that means that comparing coefficients, a plus b has to be 0 because there's no x squared term on the left. C has to be 1. A has to be 4. And so therefore, b has to be negative 4. And so there's our values for a, b, and c. And so from partial fractions, we get that this is equivalent to 4 over x plus negative 4x plus 1 over x squared plus 1 dx. Now the first one, that's just a logarithm. The antiderivative of 4 over x is just 4 logarithm absolute value of x. The next one, well, we need to decide what we want to do. Well, we can substitute for the bottom and see what happens. Well, if I substitute for the bottom, then I need to have a 2x, or at least an x factor in the top to absorb with the dx to make the substitution work, but I don't. I have it in one piece, but not the other. But that seems to suggest that it might be best to split that up then. So we can split it up as 4x over x squared plus 1, and the other piece is 1 over x squared plus 1. And now this first one, antiderivative, is just 4 logarithm absolute value x. Now the second one we could do by substitution, u equals x squared plus 1. And then it would antidifferentiate to a logarithm. You may be able to do this one in your head by this point. And the third one, the antiderivative of 1 over x squared plus 1 is just arctan of x. And then we have a plus c added to all that. And so there we go. We've used partial fractions, and then at one point we had to do a substitution right there. I didn't put the details of the substitution in because sometimes you can be able to do these things in your head without writing them out explicitly, but it would be a substitution of u equals x squared plus 1 to get that middle term. Okay, let's look at the next example. Now with all these examples we're doing, it's a good idea to pause the video right before I'm about to do it, and then for you to work on it on your own. And then when you want to get some hints or see how I'm going to do it, then you can play the video at that point in time. So this next example, pause the video now if you haven't done so already and worked it out. So here we've got a product of two trig functions, sine to a fourth power and cos to a third power. I'd like to have even powers of these trig functions because my Pythagorean identity, sine squared plus cos squared is 1, helps me rewrite even powers of one in terms of even powers of the other. Now, if I do have an odd power appearing, such as in the cosine case, I can always get rid of one of them. And I can get rid of one of them by doing a substitution for the sine function, because then when I substitute u for sine, I get a cosine appearing, which has to be absorbed with the dx in order to make the substitution work, which means I can borrow one of the cosines, pair it with the dx, and get that substitution to work. So let's do that. U is equal to sine x du is equal to cos x dx. Let's do the limits as well, since this is a definite integral. So the original limits of integration were upper limit of pi by 2 and lower limit of 0. And in this case, the u value when x is pi by 2 is sine of pi by 2, which is 1. And u is, when x is 0, is sine of 0, which is 0. So this becomes the integral from 0 to 1. Now sine, we've just substituted by u, so that's u to the 4th. The cos cubed, well, one of the cosines I borrowed with the dx, so that leaves a cos squared left. A cos squared left can be written as 1 minus sine squared, and sine is u, so this can be written as 1 minus u squared, and then cos x dx is du. So this shrunk all the way down to just the integral of a polynomial. So this becomes from 0 to 1, u to the 4th minus u to the 6th du, which is 1/5 minus 1/7 or 2/35. So let's look at the next example. E to the x sine 2x dx. Now here's a product of two functions by parts. If we recall the method of by parts, it allows us to attack this one, and we had to do by parts twice on this one. So let's recall how we handled this example before. We take u and dv. So u is going to be the thing we're going to differentiate. dv is the thing we're going to anti-differentiate. Since the exponential function is really easy to anti-differentiate, I'm going to take that to be dv. And u is sine 2x. So du is 2 cos 2x dx. And v is e to the x. And now, in what follows, I'm going to let I denote that integral. And so we have that I is equal to, from by parts, it's e to the x sine 2x, where it's the product of these two, minus the integral of the product of these two. Now we don't seem to have made the integral any easier. We started with an exponential and a trig function. We still have an exponential and a trig function. But if we apply by parts again, we can turn that cosine back into a sine function and then get an equation relating our integral to itself, which we can then solve. So using algebra, we can then solve what the value of the integral is. So by parts again, take u to be cos 2x. And of course, for doing this, I'm going to take that 2 that's in front and I'm just going to move it outside there. And so then dv is e to the x dx. du is negative 2 sine 2x. And dx. And then v is e to the x. And so I is equal to e to the x sine 2x minus 2 times, and again the method of by parts, we've just worked out all the values of u, du, v, and dv. Then we get this as the e to the x cos 2x, and then we have a minus the integral of the product of the things on the bottom, but there's already a minus there, so it would be plus 2 times e to the x sine 2x dx. And this is the interesting part with this example, is that is the original integral that we started with. So that's just I. So what we have found is that I is equal to e to the x sine 2x minus 2e to the x cos 2x. And so we have a minus 2 times a 2, so that's minus 4 times I again. So now I can use algebra to solve for what I is. That's 5I, bringing the negative 4I to the other side. Becomes 5I. And now dividing by 5 gives us that the integral is 1/5 e to the x sine 2x minus 2/5 e to the x cos 2x. And so there is the value of our integral.